In this experiment, a position time graph is used to analyze the motion of an object over a given time interval. A position time graph shows how an object's position changes as time progresses, allowing us to visually interpret different types of motion. The slope of the graph represents the object's velocity, while changes in the slope indicate changes in speed or direction of motion. By examining the shape of the position time graph, we can determine whether the object is at rest, moving at a constant velocity, or accelerating. A straight line indicates constant velocity, a horizontal line indicates zero velocity, and a curved line indicates acceleration. This experiment demonstrates how motion can be described and understood using graphical representations rather than direct measurements alone. As you can see here, the little sliding card will give us a position over time. For our lab report for lab number 2, we're going to try to calculate our velocity by getting position and time through this graph right here. And what we're going to do is we're going to hit record, and we're going to get some position right there. And we kind of want to just get 2 stops and runs, and we'll stop it right there.
So here we have our position over time and our velocity over time. So we gathered the 2 points to calculate the velocity, and the highlighted region on the velocity time graph is your average velocity for that part of the graph. So you do that for both graphs, and that gives you the mean value for both of those displacements in the graph.
For our T1, we got 1.75. And for our Y1, we got 1.88 for our first point. Our second point, we got T2, which is 3.2, and our Y2, which came out to 0.13. And then we're going to use the third point right here with our T3. We're going to do 4.9, and our Y3 came out to 1.86. And if you go down here, the average velocity that we got for point 1 and point 2 was, it's not there, but we had a minus 1.11. And for our second average for the velocity of point 2 to point 3, we got a mean of 0.05. So a real life scenario or example of what we're trying to demonstrate with the graph would probably be like a basketball player running suicides. The basketball player will start right here, and he would run down the line, touch the line, and run back. And then he would touch the next line and come back. So a good example would be a basketball player when he's doing his suicide sprints. He'll be running in a constant velocity to one point, stop there briefly, and then run back to the other point and stop there briefly.
Hi everyone. Today I'll be presenting the results of Physics Lab 2, which focuses on constant velocity and motion analysis using position versus time graphs. In this lab, we use a glider on air track and a motion sensor connected to Capstone software. The goal was to analyze the motion on the glider, identify key points on a position versus time graph, calculate velocity manually using slope, and then compare those values with the velocity graph generated by the software. On slide 2, the team recorded the key points from position versus time graph. We identified 3 important points: the initial position, labeled point A, the changing direction point, labeled point B, and the final position, labeled point C. For point A, the time was 1.75 seconds and the position was 1.88 meters. For point B, which represents the turning point where the glider changes direction, the time was 3.2 seconds and the position was 0.13 meters. For point C, the final position we analyzed, the time was 4.9 seconds and the position was 1.86 meters. From these values, we can see that the glider first moved from about 1.88 meters down to 0.13 meters, meaning it was moving toward the center. Then, after point B, it reversed direction and moved back toward approximately 1.86 meters. In physics, velocity is the slope of the position versus time graph. That means velocity equals change in position divided by change in time. In slide 3, for the first section from point A to point B, the change in position was 0.13 meters minus 1.88 meters, which equals to negative 1.75 meters. The negative sign tells us the glider was moving toward the center. The change in time was 3.2 seconds minus 1.75 seconds, which equals 1.45 seconds. So velocity equals negative 1.75 meters divided by 1.45 seconds, which gives us approximately negative 1.2 meters per second. That means during this interval, the glider was moving toward the sensor at a constant speed of about 1.2 meters per second. Now for the second section, from point B to point C, the change in position was 1.86 meters minus 0.13 meters, which equals 1.73 meters. The change in time was 4.9 seconds minus 3.2 seconds, which equals 1.7 seconds. So velocity equals 1.73 meters divided by 1.7 seconds, which gives approximately 1.01 meters per second. This time, the velocity is positive, meaning the glider was moving away from the center. So we can clearly see the sign of velocity changes when direction changes. Next, we compare our hand computer velocities with the velocity values generated by Capstone. On slide 4, we have comparison with Capstone velocity graph. For the first section, the mean velocity from Capstone was 0.05 meters per second, while our hand calculation was negative 1.2 meters per second. For the second section, the mean velocity from Capstone was 0.07 meters per second, while our hand calculation was 1.01 meters per second. When we calculated the percentage difference, we found 104.16% difference for the first section and 93.07% difference for the second section. These are very large percent differences. This suggests that either the velocity graph may not have been selected correctly, the averaging tool might not have been applied properly, or there were experimental errors such as sensor alignment, lag, or noise in the data. The important concept in this lab is understanding that velocity is directly related to the slope of the position versus time graph. When the line slopes downward, velocity is negative. When the line slopes upward, velocity is positive. When the slope is constant, velocity is constant. The turning point represents where velocity changes sign because direction changes. Even though our percent difference were high, this lab helped reinforce the connection between slope and velocity, as well as the importance of sign in dimensional motion. In conclusion, this lab demonstrated how we can determine velocity by calculating the slope of a position versus time graph. We identified key motion points, computed velocities manually, and compared them to software-generated values. The main takeaway is that velocity depends not only on magnitude but also on direction, and that the slope of a graph provides both pieces of information. Thank you.